is created, the code is deployed onto that machine, it receives the input from the HTTP computer, computes the result, returns the output, and then crucially, the really important bit, the machine is destroyed. That has implications for the application and how it's constructed. Principally, there's this. The application cannot have internal state. It cannot remember what happened the last time the function was called without having an outside service like the database. More pragmatic engineering limitation that will probably become less true with time, which is that serverless instances are low-powered, short-lived machines. They're low-powered in the specific case of AWS Lambda. They've only got 1.5 gig of RAM at most, and crucially, the function has to finish in 300 seconds. If it doesn't finish in 300 seconds, tough. The computer shuts down. You don't get past the result, you get no result. That constrains what you can do. But if you're thinking pure functions, low-powered machines, that sounds a little bit like the macros in MapReduce. You think along the right lines for the rest of the talk. This is a kind of science, and we would like to do this stuff on serverless for many things that are separate. So how can we do that? I just want to really, the purpose of this talk is to advertise someone I was not involved in, I think is wonderful. This is a paper that came out of Riselab Berkeley about fundamentally it's about a new Python tool called PyRen, that's part suggested paper. The paper's really interesting, and you can tell the title of the goal here is to democratize and make more inexpensive what has traditionally been quite expensive and complicated, namely distributed computing for analytics. PyRen can be seen as an alternative or a lightweight replacement for tools like Spark. How so? Well, PyRen essentially abstracts away serverless as a back-end computational engine for embarrassingly parallel operations. So you've got a very simple code snippet here. We instantiate an executor. This is an object that knows how to on-demand create Lambda instances, and then any function that we can map across inputs. So this is the last line here is the thing you might normally write in this convention. If you can turn that into a Python map function, and we're mapping expensive function across lots of inputs, and we get the result quickly and inexpensively with on-demand infrastructure. That's what's going on in the background here. We'll have a couple more minutes because, yeah. So as a specific example, you can imagine scraping a website for lots of URLs. That's something I do day to day. Perhaps a more interesting and classical benchmark is Shakespeare, Wikipedia, whatever. We've got a Lambda function in there, Lambda the anonymous function, not Lambda the AWS thing, that knows how to count words, and then we collate results. And all the computation is happening in the cloud. Just as a rough idea, all benchmarks are dubious at best, but this is the benchmark reported by PyRen folks. A few hundred AWS Lambda instances, roughly equivalent to 100 node Spark clusters, so that's kind of classical, embarrassingly parallelizable analytics distribution. But that's not the point. The point is, I was able to do that on my own without calling Adolf, without calling a data engineer to help me get set up, without speaking to the people who are code cursor engineering to make decisions like I want to stand up a long Spark cluster. Machine learning, of course, not all of it is embarrassingly parallelizable, but some of it is. I think the most obvious example is hyperparameter search. That's, of course, when you essentially try lots of numbers and see which one's the best. That is embarrassingly parallelizable. As long as training you can do it in under 300 seconds, you can use PyRen as the executor for that kind of job. It also raises the interesting possibility of mapping gradient descent across these things. Not all implementations of gradient descent are trivially embarrassingly parallel, and there are, of course, communication costs of sending live batches of data around the nodes. So this isn't as simple as mapping a URL scraper across a PyRen executor. Additionally, in the real world, distributed systems involve stragglers, they involve faults, and you need a distributed gradient descent algorithm that is robust against that, let's say, asynchronicity. I'm working on this right now. If anyone else is working on this, I'd love to talk to them using serverless as the back end of those kinds of fundamental machine learning calculations. Finally, PyRen is, I think, one of the several guarantees in a distributed system. You only have nodes, one of them's going to fail. PyRen won't have that, unfortunately. So it's up to you to do that kind of bookkeeping that's necessary for that. So this is not a Spark alternative. I'm not saying you don't need Spark anymore, but this is a lightweight, fun thing to play with. I think it's very useful for machine learning people and data scientists to be aware of. And that's because, frankly, it raises the possibility of the exciting future where the data engineer and the data scientist are friends again because they no longer have to argue about contention on an expensive distributed system. Thank you very much. Hi everyone, my name is Chi. I'm a software engineer at Google and I work on TensorFlow. And today I'm going to take you through a quick tour for how to debug, monitor, and examine your TensorFlow-based machine learning models using TensorFlow and suite of visualizations. They may only give you 10 minutes, so I'm going to assume some background on TensorFlow as well as on convolutional neural nets. I'm also going to very quickly gloss over some code and leave that for lab and documentation. And let's see, today we're going to build this very simple model for classifying MNIST handwritten digits. This is a very classic image recognition problem. It's a very simple model. We just have a convolutional layer and a fully connected layer. The first thing that we probably want to do is, of course, construct our model in TensorFlow. We build a graph, and then we're going to validate that it's correct. Of course, TensorFlow is a graph-based API, so we first construct a graph using various hops. In this case, we introduce this const UDOB and a couple variables, as well as a fully connected layer. And then we're going to validate whether or not our graph is correct. And how we do that is we pass our graph to this file writer object that writes the graph to disk. And TensorFlow will subsequently read that file, that events file on disk, and visualize it with its graph explorer. And at a glance, this is our graph explorer, and it looks really chaotic, right? There are a lot of different hops. And if I look carefully, I can make sense of it. But really, this is pretty messy. So what I'm going to do is actually quickly. I could collect some audio data, but not today, but that's useful, for instance, if you have an audio-based model. I'm going to also collect some histogram data that tells me the distributions of values of various tensors I'm interested in. For instance, maybe the weights of my layers, just to see, just help me monitor the model over time as it trains. And again, data is saved in a log directory. So let's see our images first. They generally seem to be correctly inputted into the model. But when I look at my scalar data, I realize that my accuracy isn't really increasing over time. It sort of plateaus at this very kind of tepid value of 0.11. So something is awry. If I go and look at my histograms or my distributions dashboards, I realize that all my activations and weights are 0. And that kind of hints us at our error, which is that I accidentally forgot to initialize these variables with meaningful values. I initialize them to 0. So we instead initialize these values and make a truncated normal distribution. And then let's see what happens next. So we rerun our model, and then we realize that accuracy still isn't really improving. But we can validate through the distributions dashboard. Examine various layers just for fun. For instance, we can take a look at the Maxwell layer just to see how it looks like. And this should be visualized as an image. There we go. So it looks kind of like a smooth and version of rendition, which is maybe what you kind of expect from a Maxwell operation. It's kind of fun there. Other things that we can do are we can go back to our TensorFlow graph and perhaps examine performance. So for instance, we're interested in maybe looking at one of our runs of TensorFlow. And for instance, we're interested in which hops take up the most time. We can visualize that. We can visualize which hops take up a lot of memory. We can also visualize what devices each of these hops run on. In case, for instance, we're running on a GPU cluster, not in this case, but you can imagine how that could be useful. We can also do something else, which is we can optimize our parameters. So we can actually run TensorFlow, our TensorFlow model, using various, for instance, loading rates and dropout rates, and then compare them, and then visualize them within a single tensor board. So, for instance, here we can kind of zoom in our scalars charts and see how our different runs are doing. If we're not satisfied by point metrics, we can also utilize precision recall curves to evaluate trade-offs between precision and recall. This is, I think, a pretty standard sort of make this trade-off between precision and recall. Maybe to put it concretely, one example of this is, say we're developing a model to detect cancer cells. Do we value our model being able to recall as many cancer cells as possible about all true cancer cells, or do we value our model being more precise about what it deems to be a cancer cell out of all the cell it does deem to be cancer cells? So TensorBoard lets you do that. The one last feature I want to sort of demo to you guys is the embedding projector, which embeds arbitrary tensors of various dimensions into this 3D space. In this case, I'm visualizing an embedding of the digits, and I can maybe make this more lucid by coloring by label and then turning on night mode. And I can sort of just explore this data set a little bit. You can see how maybe the 9s and the 4s are kind of close together, and a couple of them interspersed. So, in general, TensorBoard contains all these rich visualizations for you to explore your data, monitor, and examine your model. And I hope they help you with your machine learning endeavors. The last thing I want to mention is this is really a team effort. Some of you are not here, including me. And for more information, please refer to our GitHub repository, TensorFlow/TensorBoard. Thank you.